In our previous lesson, we discussed equations and what it means to solve an equation. That is, to find the values for the variable that make that mathematical statement true, that one side is indeed equal to the other side. With an inequality, it's pretty similar, except that this time it's a mathematical statement that compares algebraic expressions. I'll just write that abbreviated. It compares expressions using symbols such as greater than, less than, greater than or equal to, less than or equal to. So that's not anything new. We've seen a lot of inequalities before in our math careers. We may have seen something like 4 is greater than 3. That's an inequality. Or to say something like x is less than or equal to -2. Or something similar to some of the warm-up problems that you see above here that you may have had a chance to work through already if you had the notes printed out. Something like 5x minus 7 is greater than 3x plus 9. Something like that. That's still an inequality. These are all inequalities. Now, in this course, we're going to use something called interval notation. So I wanted to kind of just highlight what that interval notation refers to. So if I said, for example, let's take something like x is greater than 8. X is greater than 8. Well, let me just really quickly just graphically show you what x is greater than 8 looks like. Well, if we have our number line here and we said this is 8, we're saying x can be any number that is greater than 8. So what we've often seen is a hollow circle like this and shading in the number line or drawing above the number line like that, just to indicate x can be any number that is greater than 8. Well, when it comes to interval notation, we would express the same inequality just using a different notation. We would say 8 to infinity with parentheses around each of those. And if I had that same number line here and I wanted to show that same number line, instead of me putting an open circle at 8, what I could also do is just do the parentheses notation itself here on the number line. So this would be interval notation. It's this way of expressing the same inequality or a range of values here. Because again, we're trying to indicate a range of values that satisfy that inequality. We're saying x can be any number that is greater than 8. So we're shading in any of the numbers that are greater than 8. What about if I had something like x is less than or equal to, let's suppose, let's just say 1. Something like x is less than or equal to 1. Well, what would that look like? Well, again, on our number line, we would write 1 and we would say any value that is less than 1. So again, solid circle here, and we're shading in the values that are less than 1. And in interval notation, what we want to do is we'd want to indicate here 1 going to infinity. And we're going to put a bracket, excuse me, that is wrong. That is absolutely wrong. Sorry about that. We have negative infinity going to 1, putting a bracket around that 1, and a parentheses around the negative infinity here. Because we're trying to say that from all the values from negative infinity all the way up to and including 1 satisfy that inequality. Now, a couple things that we should note here. First off, when do we use a parentheses and when do we use brackets? Parentheses is when we don't include that number. So in this previous example here, we are not including 8, right? We're not including 8 as part of our solution set. That is to say, 8 is not greater than 8. Only the numbers that are greater than 8 are greater than 8. Whereas when I use a bracket, I am trying to say that we are going to include that value as part of our solution set. We're including 1. And again, if I wanted to write this here without using a solid circle, I could just put a bracket here around 1, right? So we're trying to say we're including 1 as part of our solution set. What that also means is that whenever there is infinity, we are always going to put parentheses next to the infinity or negative infinity. Because infinity is a concept. It's not a quantitative value that you can actually count to. So we can't actually include infinity into our set. We just want to indicate we're including all the numbers going in that direction, that our numbers are increasing or decreasing without bounds. That's what we're trying to represent there. So interval notation is a way of expressing inequalities using a separate notation that we will be using primarily moving forward. And again, parentheses mean we are not including the value. Brackets mean that we are. So let's go ahead and try one example here. Let's try something like number 1. Okay, we'll go ahead and try number 1. So for number one here, we're going to solve this inequality the same way that we normally would solve an equation. So we're going to move all of our variable terms to one side and isolate it. So I'm going to go ahead and I'm going to just go ahead and just subtract 2/7 x from both sides. So we're left with a 5/7 x over here. And I'm going to move that -2 to the other side. In other words, I'm going to write the inverse. I'm going to add 2 to both sides. So 3 plus 2 is 5. Now I'm going to multiply both sides by 7 over 5, or the reciprocal. And that way I can isolate my variable. And that means I've got 7 is greater than 5, not 5, 7 is greater than x. Now, before writing interval notation, I should note that I want to write this in the correct order on the number line. So I'm going to say x represents any value that's less than 7. And if I were to draw this on the number line here, I could say, okay, here's my 7, here's 6, here's 8. And x represents all the numbers that are less than 7. Or again, if you don't want to use an open circle, parentheses, less than 7. In an interval notation, I would say -infinity going to +7, parentheses. And that would be my solution. Okay? Well, now that we know how to solve an inequality and how to represent our solution using both interval notation and using a number line or graphing our number line, so you know what I'm referring to when I ask for that, let's talk about what a compound inequality is. And all a compound inequality is a combination, all right, it's a combination of two or more inequalities. So it's just a way of combining two or more inequalities in a single statement. And there are two distinct types of compound inequalities that we need to be familiar with in this course. The first is what we call a conjunction. I'm going to just do this in a different color. So a conjunction is something such as the following. I'll give you an example. Something like -infinity to 6 bracket. So we're saying all the numbers from -infinity up to 6. And this upside down U symbol here is a way of saying and 1 to infinity. Now let's break this down for a second. What are we saying here? We're saying if I had a number line and we want to indicate our solution set is going to consist of all the numbers from -infinity up until 6. So let's do that. And I'm going to highlight this with this color. You know what? Let me actually start with something a little bit lighter. So from -infinity all the way up until 6. All the numbers from -infinity to 6. That's what we're saying there. Okay, and we're going to put a bracket here because we are including 6. Now, what about the second solution set? And we're also saying we're going to include the numbers from 1 to +infinity. So if I said 1 here, I'm going to highlight all the values from 1 to +infinity. I'm going to put a parentheses around here because we're not including 1 as part of our solution set. Our final solution set is going to represent all the numbers that represent both solution sets. So all the numbers here. So we would say our final interval 1 to 6 bracket. I don't know if you can see that. You know, I'll just rewrite it over here because I want to make sure it's clear. So 1 to 6 bracket. That is how we would express this. Now let's make sure we understand what we're saying here. The conjunction, or the interval that satisfies this conjunction, which is a type of compound inequality, is the range of values that satisfy both of these inequalities up here. So you can think of it as, let's say I were holding a party and I wanted to, and one person were saying, hey, we're going to include all the numbers that are less than or equal to 6. And the other person saying, well, I only want to invite people that are greater than 1. Well, the final guest list is only going to consist of those who satisfy both of these conditions. This is why we call this an intersection. If you kind of think of this as like a Venn diagram, those that satisfy both of these conditions. And the numbers from 1 to 6 are the only values that satisfy both. That's why we call this a conjunction. One way of thinking about conjunctions is also to use the word and to describe this. The values that are less than or equal to 6 and greater than 1. Well, what's the other type of compound inequality? We have what's called a disjunction. So something like this might be, let's suppose we had -infinity this time going to 2. Let's make this inclusive. And This symbol here, this U, which stands for union, which I'll often use to also say or, 3 to infinity. Like, take a moment and pause the video right now and draw out this number line and make sure you see what this solution set looks like. This compound inequality would include all the values going up until 2, bracket, and all the numbers greater than 3, non-inclusive, right? So we can clearly see here the difference. Now we're only including the numbers that are less than or equal to 2, but greater than 3. This is what's known as a disjunction because you can think of this as kind of an or. It doesn't have to satisfy both of these conditions. It only needs to do one. So clearly there are only numbers that will satisfy being less than or equal to 2, and there will be other numbers that are greater than 3. So this is known as a disjunction. When we're solving a compound inequality, it's important to remember that we're just solving two different inequalities. So you have a couple of options here. If suppose you were doing number 1, what you could do is you could set this up as 0 is less than or equal to 2 minus 3 times x plus 1. In other words, I can go ahead and highlight this and say this is one inequality that I want to solve. And then you could also say I also want to solve this inequality here. So say 2 minus 3 times x plus 1 is less than 20. This is my second inequality that I want to solve. Solve each inequality, where we're just breaking this up into two separate inequalities, and then bring our solution sets together. That's one option. If you're like me, though, you want to kind of do this a little efficiently. Oops. You want to do this a little efficiently. So I'm actually going to go ahead and just solve this all as one, keeping everything together. And this is totally fine. You just got to make sure that you remember that whatever you do to one, you've got to do to all of them. So what I mean by that is we're still going to isolate x. We're trying to get this by itself. So we're going to start by subtracting 2. That means we're going to subtract 2 here and also 2 here. And again, this isn't really anything too different. This is just saves me the time of having to rewrite two different inequalities. So I've got negative 2 is less than or equal to negative 3 times x plus 1 is less than 18. Now I'm going to divide everything by negative 3. And this gives me 2/3. And again, because I divided by a negative value, anytime you divide or multiply both sides by a negative value, you're going to flip that inequality symbol. And we got negative 6. Now from here, I'm almost done. I'm just going to subtract 1 from both sides. So on this left side, 2/3 minus 1 is negative 1/3. Negative 6 minus 1 is negative 7. And I want to rewrite this in the correct order. So we're going to say x is greater than negative 7, but it's less than or equal to negative 1/3. I draw this on my number line. I'm going to say negative 7, negative 1/3. We're going to put parentheses here, brackets here, shade and everything in between. So ask yourself, is this a conjunction or disjunction? And if you said conjunction, you would be correct. It is the intersecting region of these inequalities. So we can write our final solution as negative 7 going to 1/3 inclusive there. Oops, negative 1/3. We're boxing that. Okay. Go ahead and try to do number 2 now on your own. Pause the video and try number 2. And I won't work this out. You can check my scanned solutions, but know that I will have negative 9 to 9 as my solutions. So you can box those if you wanted to check your answer. Now, the last type of inequality I want to talk about today are absolute value inequalities. And if you remember in my last video when I talked about absolute value equations, when I said something like the absolute value of x is equal to 4, what I'm saying here are two different things. I'm actually saying that x is equal to 4. That makes sense. But what also works? X is equal to negative 4, because we know that once we take the absolute value of negative 4, we get 4. So the absolute value of x being equal to 4 is actually a piecewise function, or it's a way of expressing two separate equations. Well, what about with inequalities then? Well, it's the same thing. If I say the absolute value of x is greater than 5, what I am saying on one hand is that x is greater than 5. That makes sense. X can be any number that's greater than 5, and that original inequality is satisfied. But what am I also saying? I am also saying that x could be less than negative 5. Now think about this for a second. Why would it be less than? Well, on one hand, algebraically, you could think about flipping the sign as we talked about in the previous problem because you're dividing or multiplying by a negative number. But this is what is required in order for this absolute value inequality to work. That is to say, try plugging in a number that's less than negative 5, something like negative 10. If I said negative 5 here, something like negative 10. Is the absolute value of negative 10 greater than 5? And the answer is yeah. So we actually see that there's an entire interval of numbers that satisfy this original absolute value inequality. So how many inequalities have I come up with here? 2. So we can see that an absolute value inequality is simply a compound inequality. That's all we're saying here. And we could write this in interval notation as negative infinity to negative 5, parentheses, union 5 to positive infinity. So greater than inequality is simply a disjunction. Well, what about less than? Let me do this in a different color. What about less than? If we did absolute value of x is less than 5, well, again, on one hand, I will have x is less than 5. That's the original equation if we just say x is less than 5. But what also could be true? X is greater than negative 5. Well, here now, if I write this in interval notation, I would say that x would be all the numbers, if I draw, let me just draw this number line so you can see it, from negative 5 to 5. All the numbers that are greater than 5, but less than positive 5. So it includes all of these numbers in between negative 5 and 5. So what do we have here? This is a conjunction. So you'll learn a lot of silly phrases in math just to help you remember things like SOHCAHTOA or all students take calculus, for example. One thing that you can use to help you remember greater than and less than with absolute value is writing something like, this is greater than. It's an or situation. Less than could be written as less than. That's ridiculous. I know, right? You might be looking at this and rolling your eyes, but I promise you, this could come in handy when you're thinking about how to solve compound inequality that is an absolute value inequality. Let's try a quick example, something really, really basic. Let's try something like the absolute value of x minus 5 is less than 2. Ask yourself, is this a conjunction or disjunction just by looking at it? We know that this is a conjunction, less than. So we can say something like x minus 5 is less than 2, but it must be greater than negative 2. Well, this makes it quite easy to solve. Add 5 to both sides. That's 7. That's 3. Interval notation, 3 to 7. Well, what about something like absolute value of x minus 5 is greater than 2? Greater. This is an or situation or a disjunction. So I can write this as x minus 5 is greater than 2, but it's got to be less than negative 2. Here we see that x is greater than 7, but less than 3. Well, wait, hold on. Does that actually work? X has to be less than 3, but greater than 7. What we actually see here, if we draw this on a number line, is saying something like x is greater than 7, but it's got to be less than, not negative 3. It's got to be less than 3. So we've got this here. So we see the disjunction. So in an interval notation, we'd write this as negative infinity to 3, union 7 to positive infinity. And let's just make this a little bit smaller so we can all see that. Okay. And hopefully this has been helpful to think about how to solve inequalities, including compound and absolute value inequalities.